All right, so let's move on to the last section for the week, section 3.6. Section 3.6 deals with derivatives of inverse functions. So first, let's do a little review of inverse functions. Let's take, for example, f of x is x cubed, and f inverse of x is the cube root of x. So these are inverse functions because when you compose them together, they kind of cancel each other out. Like if you do f of f inverse, what am I saying kind of for? They literally cancel each other out. They give you x back, right? So you whatever input you gave, you get it right back again. If this was like 5, this would be 5, right? Because the f and the f inverse literally cancel each other. That's the whole idea of canceling, actually, is always just composition of inverses. So like in this case, if you take the cube root of x and you cube it, you get x back, right? If you take it in the other order, like x cubed, and you take the cube root, you get x back again, okay? That's what inverses do. Now, the other thing about inverses is if you have one number, let's say square, is f of some other number, let's say star, then star will be f inverse of square. So if for f you input star and you output square, then for f inverse you will input square and you will output star. F inputs and outputs swap. And so this allows us to rewrite things involving one function, rewrite them in terms of their inverse function. So for example, if you have y equals f inverse of x, say we want to find the derivative of y with respect to x. Well, first let's rewrite it as f of y equals x. Okay, that's rewriting it, swapping the input and the output. You could also think of this as applying f to both sides of the equation, and on the left you get f of y, and on the right f of f inverse cancels out and you just get left with x back again. So do that. Then we can take the derivative of both sides using implicit differentiation. So on the left, we can do like a composition of functions. We can do the chain rule. So this is f of y, right? So this is a function of a composition. So the way we'll do it is first do the derivative of the outer function, leaving the inner function alone, and then we'll multiply by the derivative of that inner function with respect to x. So there's our left side. The right side is 1. So what's the derivative of y with respect to x? It's just 1 over f prime of y. Well, that's not particularly satisfying because what is y? It'd be nice if we could say, starting with y equals f inverse of x, what is the derivative of y with respect to x? Well, all we need to do is a substitution. This involves y, but to get it back in terms of x, replace it with f inverse of x, which is equal to y. So this will be 1 over f prime of f inverse of x. Now this is a little bit surprising. Every time I look at this, that's our answer, by the way, and this kind of is this is like a general rule. It's another differentiation rule that's specific for inverse functions. Every time I look at this, though, I get confused because it looks like you're composing the inverse function and the original function, f and f inverse, but technically you're not. You're composing f inverse with the derivative of f, not with f itself. So there is no canceling of functions that will happen here unless one of them is like the exponential function, maybe, and then its derivative is itself, and it might not cancel, which actually is an example I want to look at next. So this is not some sort of canceling composition. This is, in general, this should give you something besides just x. However, for the example I want to look at, let's take y equals the natural log of x. This is a classic example of an inverse function. We often deal with the natural logarithm as the inverse of e to the x. So we can write e to the y equals x. Perform that, and then think about it that way. Actually, here, no, I don't want to perform the same stuff we did over here. What I want to do is say, in this case, the inverse function we're talking about is the natural log, and the original function that we would have had is the e to the x function, right? So what we're going to do is use this rule for the example and get y prime will be 1 over the derivative of f, which in this case is e to the x, composed with So e to the power of something composed with the f inverse, which is the natural log. And we get that. And then in this particular case, the e and the natural log cancel out, and we get 1 over x, which is the right answer, right? If you started with natural log, its derivative should be 1 over x. That's what we found before. So that was basically sort of doing that, but using this rule. Let's apply that rule to something else in the next video.